Off-bow, Pauli, and Hund's rule. Hund's rule just says to fill degenerate orbitals one at a time with parallel spin. That will give you the lowest energy. So let me blow this up so it's so small. Let's try to apply these. Erase this here. Hund's rule, fill degenerate orbitals one at a time with parallel spin. All right, this is the diagram we're going to be using a lot of. The 4S, 3D, and the 4P are missing out of here. You should write that in the book. This is the fourth shell. Here. We're going to stick with this energy level diagram for multi-electron species here. So taking a look at this, if we have hydrogen, we'd use this diagram. Hydrogen has one electron. Is this valid?
No.
This is okay, but we would call it a excited state rather than a ground state. And so that's okay. How about this? Is this an excited state or a ground state?
Ground state.
This is a ground state. Does it matter if it's spin down or spin up?
Yeah.
No. In the absence of an external magnetic field, it makes no difference. You know, if you're out in the middle of a space, do you know what's right side up or upside down? No, it's the same thing. It doesn't know. And so either orientation's fine. Now, you know, if you put a magnet, you know, an external magnet, then it knows. We have an external magnet. It's called the Earth's magnetic field. Earth's magnetic field, you know, at the north pole of the Earth is the south pole of the Earth's magnetic field. And so if we have a little magnet, the north pole of our magnet will point to the south pole, which is at the top of the Earth, right? And so now it knows. Anyway, going back over here, we go to helium. For helium, the second electron should go on the 1s, and it's going to be paired and anti-parallel, like that. And so we have a 1, 0, 0 plus 1/2, a 1, 0, 0 minus 1/2. Okay, then we go to lithium. Lithium, we have a choice, a 2s or 2p. Which one should we go? 2s, it's lower in energy. 2s is more penetrating, less shielded. So it's going to go to 2s. Spin up or spin down, doesn't matter. So this is a 2, 0, 0 plus 1/2. Beryllium, throw in another 2, 0, 0 minus 1/2 electron. Boron goes to what? A 2, 1, minus 1, plus 1/2. Or, what if I did this for boron? Is that okay? This would be a 2, 1, 1, 1/2. Is that okay?
Yeah.
Yes. It doesn't matter which one of these three because they're, you know, does the atom know which is up? The x direction, the y direction, the z direction? No. So it doesn't matter. And so anyone. But traditionally we just pick the first one. And then that's boron. Carbon. It would have to fill. Is that okay? Yeah. Is this okay? Yeah. Is this okay?
No.
No. Hund's rule. Is this okay?
Yes. Yes.
No. Hund's rule.
I was saying to fill all of them up first and then
Is this okay?
No.
Hund's rule?
No.
All exclusion. This is okay. So that's carbon, nitrogen, oxygen, fluorine, neon. And so neon, we fill the entire second shell. And so it has what we call a filled valence shell. This would be called the first shell would be called the core. And so this is the core, and now we have the valence. The valence, how would you describe the valence shell? The outermost. Okay. It gets a little bit tricky. Valence, that's the Chem 4 definition. The Chem 1A definition is going to be a little bit different. Okay, but once we start filling the next shell, so we go from neon to sodium. So we're at sodium here. Once we start filling the next shell, then we have this becomes a core. Right? Now, when you think about core, filled shell, what is filled shell? Filled shells are like a filled 2s orbital, spherically symmetric. And if you have the 2p orbitals, and we got 3 2p's, one here, one coming out here, you fill up all those you fill the 3 2p orbitals, and it looks like a sphere. You know, it's spherically symmetric. It's kind of isotropic in a way. Do you see that? And so let's fill. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. And so now this is, again, this will be the core. Actually, this is the filled valence. Sorry, this will be the core. And then we'll start filling the next shell. So let's fill it up. Potassium, calcium, scandium. Okay, now comes the question. How many valence electrons does scandium have?
3.
Automatically, you'd say 3 because in the outermost shell we have 3 electrons, so it has 3 valence electrons. And it makes sense. Do you know what the charge on scandium is? +3. Scandium's fixed charge. It only has +3 as its charge. But we have to change the definition for valence electrons right now. Valence electrons are going to be defined as the highest n electrons. And so the highest n is 4. How many electrons? N equals 4. 2. And so technically we would say there are 2 valence electrons. And so one of the charges of scandium is scandium could potentially be variable charge, but one of the charges might be +1. In other words, why do we call the valence electrons the highest n electrons? Why don't we just call it the outermost shell? The reason we don't call it the outermost shell is because the subshells are getting mixed up. Do you see the subshells are getting mixed up? An n equals 3 versus an n equals 4, which one has a higher probability of being closer to the nucleus? Which one has a most probable distance that's close to the nucleus? If we go back to hydrogen, you know, this was n squared, 9 times a naught. 9 times a naught was about 4.5 angstroms, right? An n equals 4 is 16 times a naught, which is like about 8 angstroms. And so you have an n equals 4, which is about like 8 angstroms, versus an n equals 3, which is like 4.5 angstroms. So n equals 3, n equals 4, the most probable distance. This is for hydrogen. We can't compare it exactly, but just by analogy. And so if you're an oxidizing agent, what are you going to pull off? Are you going to pull off the more... Actually, are you going to pull off the less penetrating 3D? Or no, actually, let me do this as an analogy. Is there a huge difference between the 4s and the 3D?
No.
Well, the 3D is slightly higher in energy. And so the analogy I use is you're at an apple tree, and you see 2 apples there, right? And you know, you got to really kind of pull the apple off the branch to get it to, right? And it turns out there's an apple within reach, but it's a little harder to pull off than an apple a bit higher. And so should you grab the ladder, bring it over, climb the ladder, and pull the apple that's easier to pull off, or just grab the one that's closest to you? Well, it depends. If you're strong enough just to grab the one that's closest to you, why not just pull the one that's closest to you off and not get the ladder to get it, right? And so the analogy is this. Both of these are about the same, you know, just slightly different energies to ionize. And so if you're an oxidizer, what are you going to oxidize? The one that's easier to pull off because it's not as penetrating. And so I'll go out and I'm going to grab that 3D, but in order to get the 3D, I have to go around the 4s, right, and get the 3D, because the 3D are going to be much closer to the nucleus than the 4s. And so here are the 4s electrons, the most probable distance, even though it is more penetrating, but the most probable distance is out there. Here's the 3D. Here comes the oxidizer. The oxidizer is going to hop over the 4s and grab the 3D because it's easier to pluck. No. And so what's going to happen is it's going to pluck the one that's furthest from the nucleus. And which one's furthest from the nucleus? The highest N. Where does chemistry happen? Chemistry happens with the valence electrons. And so we call the 4s valence, and the 3D, since those are inside, we call those the core. And so this is really screwed up because in this shell we have both valence and core electrons. And so scandium, what happens is an oxidizer comes along and plucks off the 4s, and then easy pickings for the 3D. And so take all 3. After scandium comes titanium. Same thing happens here. Titanium can be +2. If it's +2, it loses the 4s. If it's +3, it loses one of the 3Ds. If it's +4, it loses all of them in this shell. Even though these are core, these core are totally different than this core. When I look at this core, this is filled shell. It's stable. It's a complete pie. Whereas this core, are these core electrons? No. They're lacking that stability. And so this is titanium, vanadium. Charges on vanadium +2. I knock off those 4s. +3, +4, +5. Not easy to get +5, but it can happen. Vanadium and then chromium. All right, something weird happens with chromium. You guys memorize this in Chem 4?
Yes.
Yes. What happens with chromium?
+1.
A 4s gets kicked up to a 3d. And so what we end up with is a half-filled subshell. And so this is for chromium, and you memorize this one. And the reason is because of this. You know, if you have a pie and you have 4 slices and you need 5 slices to complete the pie, you know, this is what's going to happen. What's going to happen is that an electron gets bumped up, kicked up from this up to here to complete this pie. And so we get some additional stability from this. This is called spherically symmetric. Spherically symmetric is what we call isotropic. Isotropic is even in all directions. And so if we're dealing with a half-filled set of d orbitals, it's like spherically, all the d orbitals are surrounding them. When you look at the electron cloud around the nucleus is evenly spread out, right? Versus this wouldn't be. This would be more anisotropic. If there's a slice of the electron cloud missing, is it evenly distributed? No. And so rather than leaving it at 3d4 with a slice missing, an electron gets bumped up from the 4s to the 3d to make it even. Well, what about vanadium? What about vanadium? Why not just bump up 2 of these electrons and make it even? And so vanadium, it doesn't happen because the cost of bumping up the 2 electrons is not enough. There's not enough benefit to make it worth it. And so for chromium, the cost of bumping 1 electron is smaller than the benefit of getting this half-filled, spherically symmetric subshell. Okay, that was the quick version of that. After chromium, then things go back to normal. What comes after chromium? Manganese. That's going to fill the 4s. And then? Iron. What are the common charges on iron? 2 and 3. So plus 2, we knock off the 4s electrons. Plus 3, we lose this paired electron here. And what do we end up with? So this is iron plus 3. A half fill D subshell. All right, after iron comes cobalt. Charges on cobalt? Plus 2, knock off these, plus 3. Possibly plus 4. But the more electrons you ionize, the more difficult it becomes. And so we can't ionize all these. So iron, cobalt, nickel, copper. Something funny happens with copper. Do you know what? Yeah, we're going to promote a 4s to a 3d. And now what we have is a filled 3D subshell, which is going to be totally symmetric, spherically symmetric. And the electron cloud is going to be pretty isotropic for this. And so we're going to get stability from that. And so the core could either be a filled shell, or a core could be a filled or partially filled D. And so partially filled is not as stable as a half-filled. Half-filled is not as stable as a filled D subshell in terms of core. All right, after copper comes zinc. Oh, before I leave copper, what's a common charge of copper? Plus 1 or plus 2. Plus 2 ruins this. Ruins it, right? Plus 2 ruins that. But it ruins it at a cost. But there's a benefit, and the benefit we talk about in Chem 1b. So don't worry about that. But if copper does this, do you know what else does this? If copper does it, silver does it too. But silver is, the only difference between copper and silver is you got to bump these up 1 number. So it'd be 5s, 4d. And so let's imagine silver, 5s, 4d. It's going to have 1 electron in the 5s, 10 electrons in the 4d. What's the charge on silver, the silver ion? Plus 1. Is there plus 2 for silver? No. There's no plus 2 for silver because breaking up this filled D subshell is unfavorable. This filled D subshell is stable. It'd be like taking a slice of pie out, like this. When it's half filled, you think, wow, how could a half filled be stable? No, it doesn't look balanced, right? But it's not half filled in this sense, because we don't fill the first half of the d orbitals, we fill all the d orbitals halfway. And so the other way of looking at it is slicing it down the middle this way. And so we slice off the bottom half, let's say, or the top half, and we're left with this symmetry still. That's how we're half filling it. Okay, after, this is 4s, this is 3d. After copper comes zinc. Right, sorry. Okay, what's the charge on zinc? 2 plus. Is zinc ever 3 plus?
No.
No, zinc is fixed charge, it's 2 plus, so we don't touch this shell, the subshell. And the same thing with cadmium. Cadmium is always 2 plus. And so we call those the pseudo group 1 and the pseudo group 2 elements. So these are the pseudo group 1, like the alkali metals. They have 1 valence electron. These are pseudo group 2 because they have 2 valence electrons. What are the valence electrons? Either 1 electron here or 2 electrons here. Right? And these core are especially stable. If I had a partially filled core, then it's not so stable. It can be broken up. Okay. So that was it. All right. That's pretty much it for Chapter 8. Chapter 9 is going to be a continuation of Chapter 8. And so we're going to be talking more about these electron configurations, valence electrons, core electrons, charges, that type of stuff. So I'm going to wait until we get to Chapter 9, which we aren't going to get to today. And so we'll talk about Chapter 9 probably in one day on Monday. I'm going to just zip through it on Monday. It's not that long. Do you want the summary, the rundown? Chapter 9? Let me just write it over here. This is the periodic table. This. Okay. Here, the size increases. We go down. Here, the ionization energy increases as we go up and left. Here, the metallic character increases as we go down and left. And actually, that's what, there are other things, 2 other things, but we'll leave them off for right now. Electron affinity and one more, but we'll talk about that next time. So on Monday, we're just going to be talking about the primary ones: ionization energy and size. Okay, chapter 9. And so this is related to all this orbital stuff. But right now, is that clock right?
No.
No. Okay, so we got to finish the plots. So let's go ahead and